Hello students, this is Nikhilian, Assistant Professor, Department of Civil Engineering, IIT, Mangaluru. Today in this session, I am going to discuss about limit state of collapse in flexure. So this is a new model, that is model 3. So we all know that flexure means it is nothing but it is a movement. So today we shall see what is the maximum moment or what is the maximum flexural capacity of different pre-stressed concrete members. So firstly, let us see what are the basic assumptions made in the analysis of flexural members. So these are the following basic assumptions that are required for the analysis of pre-stressed concrete beam section. The first assumption is plane section remains plane even after bending. So that is the first assumption. The second assumption is the stress strain relationship of the material are known. So in the first assumptions we will assume that the beam or a member is always plane even after it is under bending moment. In the second assumption we will assume that the stress strain relationship of a material is known, and the third assumption is the relationship between the strain in the steel and the strain in surrounding concrete is known. So third assumption is we know the value of strain of the steel and we know the value of strain of a concrete which is surrounding the steel. So apart from this, the important assumption is at the time of failure, the stress and strain of the concrete are not mutually proportional, and the shape of concrete stress distribution follows the factored stress strain curve for concrete known as stress block. So these are the basic assumptions which are made in the flexural analysis of pre-stressed concrete members. So next we shall see what are the types of flexural failures in a pre-stressed concrete member. So various types of bending failures or flexural failures in pre-stressed concrete member are given below. So first one is fracture of steel tension, failure of unreinforced section, failure of over-reinforced section, and other modes of failure. Now let us see one by one. So first is fracture of steel in tension. So when percentage of steel provided in a section is low, then the concrete in tension zone cracks leading to the fracture of a steel in tension. This can also reduced by providing certain percentage of steel in total gross area. So as per the codal provision, minimum longitudinal reinforcement needed is 0.2% of the cross-section area in case of post-tension members when high-strength deformed reinforced steel are used. Then minimum steel percent reduces to 0.15% of the cross-section area, and this failure is sudden failure. It fails without giving any warning. Hence, this failure can be called as a dangerous failure. So, the second type of failure is failure of under reinforced section. If the cross section is provided with an amount of steel greater than required, then the failure is characterized by excess of elongation of steel followed by crushing of concrete. And here the member approaches to the failure because of gradual reduction of compression zone which develops near the top edge or sometimes at the soffit of a beam, and this failure progresses towards the compression zone. Because of this, cracks will be prolongative or it is progressive in nature which increases with respect to time, hence it gives enough warning before it fails. So the first type of failure is a sudden failure, and second type of failure is a failure which gives enough warning before it fails. And the third type of failure is failure of over reinforced section. When percentage of reinforcing compressive strength of concrete and tensile strength of steel exceeds certain range, then the section is said to be over reinforced section. It fails suddenly due to crushing of concrete because the area of steel available is large and stresses developed in the steel at failure may not reach the tensile strength and may lose well within the proof stress of the tendon. And next type of failure is other mode of failure. So what is this other modes of failure? It is not adequately designed for shear P for the shear reinforcement in PSC members. So what will happen if it is not adequately designed for shear reinforcement in PSC member? Then the member may fail due to transverse load. If the principal stresses are excessive and web is thin, then web shear crack may develop, which is due to the web crushing. Inadequate transmission length is provided because of lack of bond between steel and concrete. Failure may occur in pre-tension members. If improperly designed to resist transfer force, anchorage failure may occur in post-tension members. Now let us see ultimate flexural strength of a section. So we can calculate the ultimate flexural strength of a section in two cases. One along the flange and second one is along the web. If it is a rectangular section, then ultimate strength will be lying in the web, or it can be considered as a flange because it is a rectangular section. If it is a T section or a I section, then we need to check where the neutral axis lies and what will be the ultimate flexural strength of the section. So first we shall consider ultimate flexural strength in which neutral axis lies within the flange. So this case is suitable for rectangular section and a flanged section. So flanged section means it is a T section or a I section. In T section and I section we will be having a neutral axis within its flange. So for this case, let us derive what will be the ultimate flexural strength. So let us consider a rectangular section whose overall depth is d and effective depth is small d. So effective depth means it is a depth which is measured by leaving the cover thickness. So let small d be the effective depth of a section. So this is a pre-stressing a steel, and let this be the CG, that is central axis of a pre-stressing steel, and hence it is a rectangular section. The neutral axis lies at midpoint, that is at capital D by 2. So here in the analysis, the tensile strength of concrete is neglected. The compressive stress distribution is the combination of rectangle and parabola having a maximum compressive stress of 0.45 FCK at the top fiber. So this is the stress diagram of a rectangular section. So in this rectangular section, the maximum compressive force is developed at the top fiber and it is 0.45 FCK. The average compressive stress of the rectangular section will be 0.36 FCK, 0.36 FCK, which will be acting at a distance of 0.42 XU. So this is the distance 0.42 XU, which is measured from CG of a steel, or which is measured from top surface of a cover. So D is the effective depth, or D is the effective thickness of a beam. So D minus 0.42 XU will be the perpendicular distance for average compressive stress. Therefore, the average compressive force developed in this rectangular beam is equal to 0.36 FCK B into XU, where B is the width of a rectangular section and XU is the depth of a neutral axis from a top fiber. The depth of neutral axis with respect to the bottom fiber or with respect to the CG of a tensioned steel will be equal to D minus 0.42 XU. So that is about the compressive stresses in the member. And now if I consider the tensile force developed in the member, the tensile force developed in the member will be area of this tensioned steel multiplied by stress acting along the tensioned steel will gives us the force acting tensile force acting in the member, that is tensile force in the member is equal to FPU. FPU is the ultimate strength of prestressing in steel, or FPU is the prestress in steel, and AP is the cross section area of the prestressing steel. So force is equal to stress into area, prestress acting along the steel and area of the prestressed member. So this is the compressive force developed in the member, and this is the tensile force developed in the member. And from the figure, Cu is equal to 0.36 FCK B into XU and Tu is equal to FPU into AP, that is compressive force and tensile force. And what is Cu? Cu is the ultimate compressive force in the concrete. FCK is characteristic compressive strength of a concrete. XU is the depth of neutral axis at the ultimate stage. Tu is the ultimate tensile force in concrete. FPU is the tensile stress developed in the tendon at the failure stage of a beam, that is ultimate tensile stress in the tendon. AP is the area of prestressing steel. And now, what is the moment that can be taken by this rectangular member when the compressive force is equal to this much and when tensile force is equal to this much? The ultimate moment of resistance of the concrete section can be obtained either in terms of compressive force or in terms of tensile force. The strength of a rectangular member, that is the moment resisting ability of a rectangular member, can be obtained in terms of compressive force or in terms of tensile force. So in general, ultimate moment of resistance is equal to ultimate force into lever arm. So as I already told you, we can calculate the moment of resistance in terms of compressive force as well as in terms of tensile force. So first we shall calculate the ultimate moment of resistance in terms of compressive force. So that is ultimate moment of resistance in compressive force in terms of compressive force is equal to ultimate force into lever arm. So what is the ultimate compressive force in this section? The ultimate compressive force in the section is 0.36 FCK into B into XU. So this is the ultimate or maximum compressive force developed in the member. So this force multiplied by lever arm. So lever arm is D minus 0.42 XU. It is the distance which is measured from CG of the tensioned steel. So that is the lever arm in this figure. Therefore, ultimate moment of resistance in terms of compressive force is equal to EMU is equal to 0.36 FCK B into XU. So this is the maximum force, compressive force or ultimate compressive force into D minus 0.42 XU. So D minus 0.42 XU is the lever arm distance, or it is the distance which is measured from the CG of a tension steel. Then, what about ultimate moment of resistance in terms of tensile steel? So, in this figure, for this case, for a rectangular section, what is the ultimate tensile force developed in the member? The ultimate tensile force developed in the member is Tu is equal to Fpu into AP. So, this is the ultimate force developed in the rectangular section. So, moment of resistance in terms of tensile force is equal to ultimate tensile force multiplied by lever arm. So ultimate tensile force is equal to Fpu into AP. This is the ultimate tensile force in the member, and into lever arm. Lever arm is D minus 0.42 into XU. So as per IS 1343/1980, the ultimate moment of resistance of a rectangular section or a T section in which neutral axis lies within the flange may be obtained as Mu is equal to Fpu into AP D minus 0.42 XU. So for the analysis of pre-stressed concrete member in flexure, we are going to use a code book, that is IS 1343 1980. So this is the code book which is required for the analysis of pre-stressed concrete beam under flexure. So here we are going to use table 11 and table 12, where Mu is ultimate moment resistance of the section. So Mu is the maximum moment that a section can resist. Fu is the ultimate tensile stress in the steel. AP is cross-sectional area of pre-stressing tendons, and X is the depth of neutral axis from the top fiber. So as per IS 1343 1980, we can calculate the maximum moment of resistance for rectangular section or a T section when neutral axis lies in the flange using this equation. Mu is equal to Fpu into AP into D minus 0.42 XU. So using this equation we can calculate the maximum moment of resistance for rectangular section and T section when neutral axis lies in the flange.
The value of F, Pu and Xu are determined using table 11 and table 12 of IS 1343 1980 by using a ratio called as pre-stressing reinforcement index WP, and is given by WP is equal to AP into FP divided by BD into FCK. This equations XU, that is neutral axis, and we have FPU. FPU is the ultimate stress in the tensile stress in the cable. So the value of XU can be determined using the table 11 and 12 of IS 1343. So table 11 of IS 1343 1980 gives the values of FPU and XU for pre-tensioned members and bonded post-tension members. Table 12 of IS 1343 1980 gives the value of both for the unbonded post-tensioned members. So in table 11, the value of FPU and XU are respectively given as FPU by 0.87 FP and XU by D. So this is table 11 of IS 1343 1980. So here the ratio AP by FP divided by B into D FCK. We will calculate this ratio, and these are the values. So corresponding to the obtained value of this ratio, we will get what is the value of FPU divided by 0.87 FP for pre-tension members and post-tension members with effective bonding. So these are the values. So if I get the value of this ratio FPU by 0.87 FP, then I can calculate what is FPU. Similarly, the ratio xu by d. If I get the value of ratio xu by d, then I can calculate what is xu. So xu by d is equal to this value, and d is the effective depth. So effective depth multiplied by this value, we will get what is xu. So using this table for pre-tensioning members and post-tension members with bonding, we can calculate what is fpu and what is xu. So that is given here in table. The values of FPU and XU are respectively given as FPU by 0.87 FP and XU by D. Similarly, in table 12, the values of XU and FPU are respectively given as FPU by FP and XU by D. Previous case, we calculated the ultimate moment of resistance for a rectangular.
Now let us see the second case. What will be the maximum moment of resistance or ultimate moment of resistance for a flanged section, that is T section or a I section, when the neutral axis lies in the web portion. In previous case we calculated what will be the ultimate moment of resistance for a rectangular section and T section and I section when the neutral axis was lying in web portion. So this is the web portion. So when neutral axis lies within this web portion, then we can use the equation which was obtained in previous case. If the neutral axis lies in the flange, so if the neutral axis is lying in this portion in the flange, then what will be the ultimate moment of resistance of a I section or a T section member? So here let us consider a I section member whose overall depth is D, and let the width of flange be BF and depth of flange be DF, and let BW be the thickness of the web. So here this T section can be split into two sections. One is rectangular section and second one is two rectangular sections. So I am going to consider this section as one section and this two portions of a flange as a other section. So here you can see for a rectangular section the stress diagram will be in the form of a rectangle. So this is a rectangle and a parabolic shape. So the combination of rectangle and a parabolic shape will be the stress diagram for a rectangular section, and for this two, this will be the stress diagram. So if I consider the compressive force, ultimate compressive force for this rectangular section, then the ultimate compressive force for the rectangular section will develop at a depth of 0.4 to xu from the top fiber, and the maximum compressive force will be acting along the top fiber, and the maximum compressive force is 0.45 fck. Therefore the average compressive force acting along the rectangular section of a T section is equal to 0.45 fck into B minus Bw into df, where B is the overall width of a flange and Bw is the width of a web, and df is the depth of a flange or thickness of a flange. And from here to here it is d minus 0.42 xu, which is a lever arm distance. And when I consider this rectangular section, the tensile force developed in the member is equal to tu in flange, that is tuf is equal to stress, that is pre-stress in the cable into area of the cable. So that is T or TUF is equal to FPU into APW. So FPU is the ultimate pre-stress in the cable and APW is the area of pre-stressing steel in web portion. that is APW. Similarly, coming to the other part, this portion. So here in this case, the maximum compressive stress is developed at a distance of df by 2. It is developed at a distance of df by 2. So this is overall depth of a flange. So it is rectangular in shape, therefore the centroidal axis will be df by 2. Therefore the compressive force will be acting, average compressive force will be acting at a distance of df by 2, and average compressive force C is equal to 0.45 FCK into B into BW into df, where B or BF is the width of a flange and BW is the width of a web, and df is a overall thickness or depth of a flange. Here also the maximum compressive force will be acting at the top fiber, and that is equal to 0.45 FCK. Therefore the lever arm with respect to this two portions is equal to d minus df by 2, which is equal to d minus 0.5 into df. So if I simplify this will be equal to d minus 0.5 df. Then what will be the tensile force in the member when I consider only this two sections? So the tensile force will be same, that is Fp into APF. So pre-stressing, pre-stress in the cable and cross section area of the cable. So therefore the total compressive force in the member, so the total compressive force in the member or in the T section will be compressive force of this portion plus compressive force of this portion. So compressive force of this portion is 0.36 FCK BW into XU, and this portion is 0.45 FCK BF into minus BW into DF. So it is compressive force will be the summation of compressive forces in two sections, in web and in flange. So that will be equal to 0.36 FCK into BW into XU plus 0.45 FCK into BF minus BW into DF. This is the compressive force developed in the web portion, and this is the compressive force developed in the outstanding flange portion. Similarly, the tensile force developed in the member will be equal to tensile force developed in the first section, tensile force developed in the second section. That is tensile force developed in the web portion, tensile force developed in the outstanding flange portion. FTU is equal to FPU into APW plus FP into APF, where FPU into APW is the tensile force developed in web portion, and FP into APF is the tensile force developed in the outstanding flanged portion. And the ultimate moment of resistance in terms of compressive force. So in previous case I told you the ultimate moment of resistance is equal to force into lever arm distance. So the ultimate moment of resistance can be calculated in terms of compressive force as well as in tensile force, in terms of tensile force. So in terms of compressive force, the ultimate moment of resistance is equal to compressive force into lever arm distance. So what is the compressive force, total compressive force in a T section or in a flanged, so in a flanged section? So ultimate or maximum compressive force is equal to 0.36 FCK BW into XU plus 0.45 FCK into BF minus BW into DF. This is the ultimate compressive force developed in the flanged section, and this force multiplied by lever arm distance. So what is the lever arm distance? Lever arm distance is d minus 0.5 d in df. So this is the lever arm distance. d minus df by 2, which is equal to d minus 0.5 df, that is the lever arm distance. So compressive force multiplied by lever arm distance will get ultimate moment of resistance in terms of compressive force. Similarly, ultimate moment of resistance in tensile in terms of tensile force. So that will be tensile force multiplied by lever arm distance. So it's the tensile force FPU into PW into D minus 0.42 XU. So this is the moment of resistance developed for the web portion, and this is the moment of resistance developed for the outstanding flanged portion. So 0.45 FCK BF minus BW into DF into D minus 0.5 DF. So this is the distance for lever arm distance for the outstanding flanged portion, and d minus 0.42 x is the lever arm distance for the web portion. So that is what it is multiplied here. So tensile force in web portion into lever arm distance, tensile force in flanged portion into lever arm distance of the flanged portion. Similarly here also, compressive force, this is the compressive force in the web portion, and this is the lever arm distance for a web portion. So this is the compressive force in outstanding flanged portion, and this is the lever arm distance for the outstanding flanged portion, where Fpu is the ultimate tensile stress in the tendon. Fp is the characteristic strength of prestressing steel. Apw is cross-sectional area of prestressing steel for a web. Apf is the cross-sectional area of prestressing steel for flange. That is, APF can be calculated using equation 0.45 FCK into BF minus BW, which BW into DF divided by FP. So using this equation we can calculate what is the cross section area of a pre-stressing steel that is provided in the flange. Therefore AP is equal to APW plus APF, where AP is nothing but it is the total steel present in the section including flange and web, that is equal to steel cross section area of steel in web portion and cross section area of steel in flange portion. So BW is the breadth or width of a web or a rib portion, DF is depth of a flange, XU is the depth of neutral axis. And here the pre-stressing reinforcement index is given by WP is equal to APW into FP divided by BW DFCK. So it is same as previous one. So this is table number 12, from which we can get the values of FPU by 0.87 FP and the value of ratio XU by D for the reinforcement ratio for post tensioned members as well as for the pre-tensioned members. And here it should be noted that we can get the values of FPU by 0.87 FP and XU by D for the post-tension members only when the tendons are bonded. For unbonded tendons, we will refer table 12. So table number 11 and table number 12 are available in page number 59 of IS 1343/1980. So this is table number 12. So here it is given condition at ultimate limit state for post-tensioned rectangular beams having unbonded tendons. So if the member is post-tensioned members and the tendons or cables used in the member is unbonded, then we need to refer this table number 12, which is given in page number 59 of IS 1343/1980. So here we will not only calculate the reinforcement ratio, but in addition to this we will also calculate what is the ratio of L by D, where L is the effective span and D is the effective depth. So effective depth, it is small d. So this should be a small d. So there is a mistake in the code book. So it is effective depth small b. So we will calculate the reinforcement ratio. Then we will calculate the ratio for L by D. Similarly, we will find out what is the value for the ratio Fu by FPE and the value for the ratio XU by D. So here APW is the area of prestressing steel for web, APF is the area of prestressing steel for flange, DF is the thickness of web. Then, as I already told you, AP is the total area of tensioned steel in the member. So total area of tension steel in the member includes area of steel in the web and area of steel in the flange when it is a flanged section or a I section. But we can calculate the area of steel which is provided in the flange using this formula. So APF, that is area of pre-tensioning steel in flange, is equal to 0.45 FCK into B minus BW into DF by FP, where B is the width of flange, BW is the width of web, DF is the thickness or depth of flange, FP is the ultimate strength of the cable. After evaluating APF, the value of APW is obtained as. So once we get APF, then we can calculate the area of steel provided in the web using AP minus APF. So AP, total area of steel in the section, minus area of steel in the flange, gives us area of steel in the web. And now we shall try to solve some numericals on the ultimate flexural strength of a section. So before coming to the examples, once again I am going to tell you which are the formulas you need to remember. So these are the formulas you need to remember. If it is a rectangular section, or if the neutral axis lies in the flange, if the section is a T section or if the section is I section and the neutral axis of the section is lying within the flange. See here the condition is given when the neutral axis lies within the flange, and for the rectangular section we should use this formula. We can use either this formula and this formula, or we can use this formula. So if we use these two formulas, we can calculate the ultimate moment of resistance in compressive force and ultimate moment of resistance in tensile force. Whereas if we use this formula, we can calculate the net ultimate moment of resistance in the section. So we can also use these two formulas to calculate the moment of resistance, or else we can use only this formula. So both are correct. Suppose when when the neutral axis lies in the web, then what is the formula? So when the neutral axis lies in the web, we should use these two formulas, this one and this one. So this one is the formula to calculate ultimate moment of resistance in terms of compressive force, and this is the formula to calculate ultimate moment of resistance in terms of tensile force. So these two formulas and these formulas you should remember. So if you remember these formulas, then it is very easy to analyze and calculate the maximum moment that a beam can take in this model. Okay, now let us consider the first example. A pre-tensioned prestressed concrete beam having a rectangular section 150 mm wide and 350 mm deep has an effective cover of 50 mm. If FCK is equal to 40 Newton per mm square, FP is equal to 1600 Newton per mm square, and the area of pre-stressing steel is 461 millimeter square, calculate the ultimate flexural strength of the section using IS 1343 code provision. So here it is a rectangular beam which is pre-tension. So the cross section of a beam is given. The cross section of a beam is 150 mm by 350 mm, and in the question it is given that the effective cover for a beam is 50 mm and compressive strength of concrete is, that is FCK, is equal to 40 Newton per mm square, and FP of steel is 1600 Newton per mm square, and total area of steel is 461 millimeter square. So for this condition, we should calculate what is the ultimate flexural strength of a section as per IS 1343 code provision. So first let us consider the given data. So FCK, FP, AP, B and D, these are the given data. So here it is a rectangular beam and the member is pre-tensioned member. So when the member is pre-tensioned member, we should use or we should refer table number 11 of IS 1343/1980. So what is given in the table 11? So in the table 11, the values of FUP by 0.87 FP is given. Also, the value of the ratio XU by D is given. So you remember the equation which is suitable for this condition. So it is a rectangular beam and it's a pre-tensioned beam. So just remember the formula and let us calculate the data that is required to be substituted in the formula. So first I will consider the effective reinforcement ratio. So the effective reinforcement ratio is given by FP by AP divided by FCK into BD. So all these values are given in the question. So just substitute the values of FP is 1600, AP is 461, FCK is 40, B is 150 and D is 300 mm. So the answer from this substitution is equal to 0.40. Therefore, the effective reinforcement ratio for a given section is 0.4. And now from the table number 11, the corresponding values of this ratio and this ratio. See here, the value of this ratio, the value of reinforcement ratio is 0.4. So for the value of 0.4, what will be the value of ratio FPU by 0.87 FP? So for 0.4, the value of this ratio and it is a pre-tensioned member. So see under this column it is 0.9. Similarly for 0.4, what will be the value of the ratio XU by D? So the member is pre-tension member. So refer this column. So the value of ratio XU by D for reinforcement ratio 0.4 is 0.783. So it is 0.783. So write down the values. It is 0.9 and for this ratio it is 0.783. So here we know what is FP. FP is given in the question. FP is equal to 1600 Newton per mm square. So substitute the values of FP. Therefore, FPU is equal to 0.87 into zero point 0.9 into 1600. We will get 1253 Newton per mm square. So FP is nothing but it is the ultimate tensile stress available in the cable. So ultimate tensile stress available in the cable is 1253 Newton per mm square. Similarly, considering this ratio, D is given. See here, in the question it is given that the overall depth of a section is 350 mm, but the effective cover is 50 mm. Therefore, the effective depth D will be capital D minus 50, that is overall depth minus thickness of the cover. We will get effective depth of a beam. Therefore, effective depth small d is equal to 350 minus 50, that is equal to 300 mm. So 300 mm is the effective depth of a beam. So XU is unknown and small d, that is effective depth, is known. So substitute the value of small d. Therefore XU is equal to 0.783 into 300 effective depth, that is equal to 234.9 millimeter. Therefore moment of resistance. So as I told you before, for a rectangular section and for a T section or I section, when the neutral axis lies in the flange, we can use either these two formulas or else we can only use this formula. So both are correct. So here I will use this formula as per the recommendation of IS 1343-1980. So it is a rectangular section. So I am going to use the formula to calculate the moment of resistance. Mu is equal to FPU into AP into D minus 0.42 XU. So this is the formula as per IS 1343-1980 to calculate the ultimate moment of resistance of a rectangular prestressed concrete beam. So the values of FPU is known, that is we have calculated in previous step. AP is known, area of steel, it is given. So D, effective depth, so overall depth is 350 millimeter and thickness of cover is 50 mm. So overall depth minus thickness of cover will get effective depth, that is 300 mm. Like 350 minus 50 is equal to 300 mm, and 0.42 into XU we have calculated in previous step, that is 234.9. Therefore the ultimate moment of resistance is equal to 116 into 10 to the power of 6 Newton millimeter, or it is 116 kilonewton meter. So this is the ultimate moment resistance of a rectangular PSC beam. So the rectangular prestressed concrete beam can take up a maximum moment of 116 kilonewton meter. Now let us move on to the next example. A pre-tensioned T section as a flange which is 300 mm wide and 200 mm thick. The rib is 150 mm wide by 350 mm deep. The effective depth of the cross section is 500 mm. Given AP is equal to 200 mm square, FCK is equal to 50 Newton per mm square, and FP is equal to 1600 Newton per mm square. Estimate the ultimate moment capacity of the T section using Indian Standard Code regulations. So here it is a flanged section, that is the section is a T section, and the cross section of a flange is 300 mm by 200 mm, and cross section of a web or a rib is 150 mm by 350 mm. And here it is directly given that the effective depth of a cross section is 500 millimeter. So first let us consider the given data. So in the question, FCK is given, that is compressive strength of a concrete is given, it is 50 Newton per mm square. FP is given 1600 Newton per mm square. Area of steel is given, it is 200 millimeter square. B is given, it is 300 mm, and overall depth, that is effective depth, is equal to 500 mm. Hence it is a flanged section, it is a T section member, and we don't know whether the neutral axis lies in the web or the neutral axis lies in the flange. If the neutral axis lies in the web, then we should consider the formula which we have calculated derived in second case. If the neutral axis lies in the flange, then we can consider the equation or formula which we have derived in first case. So here the most important thing is we should assume whether the neutral axis is lying in the flange or neutral axis is lying in the web. First I will assume that the neutral axis lies in the flange. So why we need to assume is when we consider the reinforcement ratio, that is when you consider the ratio FP into AP by FCK into BD, here we have a term B. So D is the effective depth whereas B is the width. So if I consider the neutral axis lies in the web, then B will be equal to 150 mm. So before calculating the reinforcement ratio, we should assume that whether the neutral axis lies in the flange or it lies in the web. So here I am going to assume that neutral axis falls within the flange. Therefore, the value of B is equal to 300 mm for computation of effective reinforcement ratio. So the width of a flange is 300 mm. So I am going to use the width of a flange as 300 mm in calculation of effective reinforcement ratio. So substitute the values in this equation. So FP is known, it is given in the question. AP is known, it is given 200 mm square. FP is 1600, FCK is 50, B is 300. So this 300 is the width of the flange because I have assumed the neutral axis is lying in the flange, and D is the effective depth. So effective reinforcement ratio is equal to 0.04. From the table, so here in this step we have got the effective reinforcement ratio is equal to 0.04. So we have assumed the neutral axis lies in the flange. From table number 11 of IS 1343-1980, what will be the value for the ratio FPU divided by 0.87 FP for the reinforcement ratio 0.04? So here it is 0.025. For 0.025, the value of the ratio FPU by 0.87P is 1. So again, remember this. This is for this column is for pre-tensioning members, and this column is for post-tensioning members with bonding. So the given member is a pre-tensioned member. So we shall refer this column, and for 0.5 it is 1. So the value what we have got for reinforcement ratio is 0.04. So let us interpolate this. So if we interpolate 0.025 and 0.5, the value for 0.04 will be 1. Similarly, to know the value of the ratio XU by D for 0.04, let us interpolate 0.05 and 0.104 to get the value for 0.04. So again, here also remember we have two conditions. One is for pre-tensioning and other one is for post-tension with effective bond. So the given member is pre-tension. So let us consider first two values under this. So if we interpolate between 0.054 and 0.104 for 0.04 reinforcement ratio, we will get 0.09. So it is 1 for Fu by 0.87 Fp and it is 0.09 for Xu by D. Therefore, Fpu is equal to 0.87 and the value of Fp is given in the question. It is 1600. So Fpu is equal to 1392 Newton per mm square. Similarly, Xu is unknown and D is known. D is effective depth of a section. So the effective depth of a section is directly given in the question. It is 500 millimeter. So if we substitute the value of 500 in the place of D, then XU is equal to 0.09 into 500, that is equal to 45 millimeter. So remember this FPU, that is ultimate pre-stress in the cable, is 1392 Newton per mm square, and the neutral axis lies XU is equal to, that is neutral axis is lying at a distance of 45 mm. So in the beginning I told you that while deriving the equation, XU means it is the neutral axis. So XU is the distance of a neutral axis, and I told you that the neutral axis, the distance of neutral axis, that is XU, is always measured from the top fiber for the condition what we have derived. Therefore, if I measure the distance of XU from the top fiber, so the section is I section. If I measure the value of XU from the top, from the top fiber, then XU will fall within the flange because the depth of a flange is 200 millimeter. The value of XU, distance of neutral axis, is 200 mm. Therefore, XU is lesser than thickness of flange. That means the neutral axis lies in the flange. Therefore, we can use the equation which we have derived in first case. The assumption that the neutral axis falls within the flange is correct. Hence, the ultimate flexural strength of the section is Mu is equal to Fpu into AP into D minus 0.42 XU. So substitute the values. Already we have calculated what is Fpu and we know what is XU. We have calculated in previous step and calculate what is the ultimate flexure of a given T section member. So substituting the values, we will get the ultimate flexure of a member is equal to 134 into 10 to the power of 6 Newton per Newton millimeter or 134 kilonewton meter. So a T section member can take up a maximum moment of 134 kilonewton meter. So let us consider one more example. A pre-tensioned T section has a flange 1200 mm wide and 150 mm thick. The width and depth of the rib are 300 mm and 1500 mm respectively. The I tensile steel has an area of 4700 mm square and is located at an effective depth of 1600 mm. If the characteristic cube strength of the concrete and tensile strength of steel are 40 and 1600 Newton per mm square respectively, calculate the flexural strength of the T section. So again it is a flanged section or it is a T section, and the cross section area of the flange is 1200 by 150 mm and cross section area of a rib or a web is 300 by 1500 mm respectively. So if we consider this, the overall depth of a section is equal to 1500 mm plus 150. So the overall depth is equal to 1650 millimeter, and the total steel the area of total steel used in the section is 4700 millimeter square, and the pre-tensioned cables or pre-tensioned tendons are located at an effective depth of 1600 millimeter. So here also they have directly given the value of small d, that is they have directly given the effective depth is equal to 1600 mm, but remember overall depth is 1650 millimeter, and the values of strengths of concrete and steel is given, it is 40 and 1600 Newton per mm square respectively. So first let us consider the given data. So these are the given data. AP is given, that is total area of steel in the section. Compressive strength of a concrete is given. Width of a flange section is given. BW, width of a web is given. D, that is overall depth is given, and thickness of a flange, that is 150 mm. So remember one thing, if it is I section or if it is a T section, the overall width of the section is equal to the width of the flange. Here the width of the flange is 1200 millimeter. Therefore overall width of the section will be 2000. Sorry, overall width of the section will be 1200 millimeter. So here I am going to consider the neutral axis lies in the web. In previous example, we had considered the neutral axis is lying in the flange, but here I am going to consider the neutral axis is lying in the web. So remember the condition. When the neutral axis lies in the web, which formula we should use? When the neutral axis lies in the web, we should use these equations. So this is ultimate moment of resistance in compression and this is ultimate moment of resistance in tension. So these two formulas we should use to calculate the ultimate moment of resistance when the neutral axis lies in the web. And the next thing is, in previous case we were calculating the reinforcement ratio. So there the reinforcement ratio was AP into FP, whereas here the reinforcement ratio is equal to APW. So when the neutral axis was lying in the flange, or when it was a rectangular section, this term was AP. That is, it was the total area of pre-tensioned steel. But here, in case of the second condition, that is when the neutral axis is lying in the web, here it is APW, that is the area of steel in the web portion, and this will become BW is the width of flange, D is the overall depth, and FCK is the strength of concrete. So remember the condition. If the neutral axis lies in the web, this term changes and this B changes. So in the formula to calculate the reinforcement ratio, we have APW. So what is APW? APW is the percentage total area of steel present in the web. So we know that total area of steel in the T section, total area of steel in the T section is equal to total steel in web plus total steel in flange. But to calculate the reinforcement ratio, we need what's the area of steel in the web. That is, we need what is APW, and we know that total steel is the summation of these two. And we have a formula to calculate the amount of steel that is provided in the flange. So amount of steel in flange, APF. So the quantity of steel present, area of steel present in the flange, APF is equal to 0.45 FCK into B minus BW into DF by FP. So all these values are known values. So 0.45 into FCK is given, it is 40 Newton per mm square. B is known, that is 1200, is B is 1200 mm minus, so BW is the width of web. So width of web is given, it is 300 mm, so BW is 300 mm. Substitute the value. DF, thickness of flange or depth of flange, it is given, it is 150 mm. Here it is given by FP. So FP, it is given in the question. The tensile strength of steel is 1600 Newton per mm square. So substitute that, we will get what is the total area of steel present in the flange. So total area of steel, that is APF, in the flange is equal to 1518 Newton, sorry 1518 millimeter square. So total area of steel present in the section is 4700 millimeter square, but the area of steel present in the flange is 1518 millimeter square. Then what is the area of steel present in the web? Area of steel present in the web is equal to total area, that is 4700 minus area of steel present in the web, so area of steel present in the flange. So 4700 minus 1518 is equal to 3182 millimeter square. So this is the total area of steel present in the web. Now considering the reinforcement ratio, so APW FP divided by BW D into FCK, that is equal to APW, area of steel in the web, we have calculated 3182, FP is given 1600, BW. So this is what I told you in the previous example. When I consider the neutral axis is lying in the flange, then this B will be the width of flange. But here I have assumed that neutral axis is lying in the web. Therefore, this B will be width of web. So width of web or rib is given, it is 300. D is effective depth 1600 into 40, that is compressive strength of a concrete. Therefore, the reinforcement ratio is equal to 0.267. From table number 11 of IS 1343. So from table number 11 of IS 1343, this table is available in page number 59. See here, for the effective reinforcement ratio of 0.265, for the effective ratio of 0.265, we should consider, or we should get the value of the ratio FPU by 0.87 FP, as well as we should also get the value of the ratio XU by D from this table. So remember, the given member is pre-tensioning member, so refer this column. Similarly, here also refer this column because it is a pre-tensioning member. So if we interpolate the values, here and here, then the ratio of FPU by 0.87 will be 1. Therefore, the value of FP is known. So substitute the value of FP. FPU is equal to 0.87 into 1600. So ultimate stress in the cable is equal to 1392 Newton per millimeter square. Similarly, for 0.265, the ratio XU by D is equal to 0.56. So the value of D is known, that is effective depth of the member, or the effective depth of a flanged section. It is 1600 millimeter. Substitute the value of D in this. Therefore, XU is equal to 0.56 into 1600 millimeter, which gives 896 millimeter. So here what I had assumed, that the neutral axis lies in the web. So the neutral axis is lying at a distance of 896 millimeter. So I already told you, neutral axis is measured from the top fiber. So overall depth of a section is 1650. Overall depth of a section is 1650, that is 1500 plus 150, it is 1650, and neutral axis is lying at a depth of 896 millimeter. So when we measure a depth of neutral axis from top fiber of a T section, it is lying somewhere here at the midpoint. See the thickness of a web flange here. So thickness of a flange is 150 mm. So 150 mm is the thickness of a flange. Therefore, the XU value is greater than 150 mm. So if the value of XU is greater than 150 mm, that tells that neutral axis is lying in the web. Therefore, the assumptions what we have made is correct. Suppose if the value of XU was less than 150 mm, if the value of XU was less than 150 mm, then we could have repeated the steps from the beginning. If it was less than 150 mm, then again we have to calculate the reinforcement ratio by assuming the neutral axis lies in the flange, and then again we need to calculate what is FPU and what is XU. So our assumption is wrong, as that the XU is greater than 150 millimeter, that is XU is greater than thickness of flange. That shows that the neutral axis is out of the flange. Therefore, the last step is to calculate the ultimate moment of resistance. So ultimate moment of resistance in compression. So ultimate moment of resistance in compression means the neutral axis is lying in the web. So when the neutral axis lies in the web, as I already told you, we should consider the second condition. We should consider this condition. This second condition we should consider. So when we consider this condition, we have two equations. So consider these two equations. So mu. So this equation is the equation to calculate the ultimate moment of resistance. in the terms of compressive force. Again, I am telling you this equation is the equation to calculate moment of resistance in terms of compressive force. So FPU, APW, XU, FCK, BBW, DF, small d and capital DF, all these values are known. So FPU we have calculated, APW area of steel in the web we have calculated here, it is 3182, effective depth it is given 1600, XU neutral axis we have calculated here, it is 896, FCK is given, B that is overall width of a section, that is width of the flange 1200 mm, width of a web, thickness or depth of a web, effective depth, thickness or depth of a web. So substituting the values for all these terms, the final value is equal to 9125 into 10 to the power of 6 Newton millimeter, or 9125 kilonewton meter. So this is the moment of resistance of a T section in terms of compression. So the T section can take a maximum moment of 9125 kilonewton meter. Similarly, we can also calculate moment of resistance in terms of tensile force. So for that we should use this equation. So if we use this equation, then we can calculate the ultimate moment of resistance of a T section under tensile force. So we have calculated the ultimate moment of resistance in terms of compressive force. Therefore, if a beam is subjected for a moment more than 9125 kilonewton meter, then beam starts failing, or the beam starts cracking, or it will undergo failure.